Artificial intelligence is a nested hierarchy, not a monolith. This video breaks open the black box, tracing the evolution from basic machine learning to generative foundation models. The timeline of AI capability shows a long period of stagnation, known as the AI winter in the 80s and 90s, focusing on expert systems. The curve began to rise in the 2010s with machine and deep learning, leading to the exponential growth of generative AI in the 2020s. This table defines the hierarchy of computational intelligence. AI simulates human intelligence using structured, rule-based systems. Machine learning discovers patterns with labeled data. Deep learning mimics the brain with multiple layers and raw data. Generative AI creates new content from massive, unstructured data. A simple decision, like ordering a pizza, illustrates how a basic neural network or perceptron makes a prediction. It takes weighted inputs, sums them, applies a bias, and fires the neuron if the total exceeds a threshold. Binary logic fails in deep networks because the abrupt step function is non-differentiable, making microscopic weight adjustments mathematically impossible. Deep learning requires smooth nonlinear curves to allow backpropagation and error calculation. Activation functions are the mathematical gatekeepers of neural networks. Linear, sigmoid, tan, and ReLU each have unique curves, output ranges, and fatal flaws, such as collapsing networks or causing gradients to vanish. The vanishing gradient waterfall illustrates signal degradation. Because activation functions flatten at their extremes, the tiny fractions multiplied during backpropagation shrink exponentially. This prevents earlier layers from receiving the signal to update their weights. The curse of dimensionality refers to the exponential expansion of problem space as features increase. As dimensions grow, data points become incredibly sparse. This sparsity means a machine learning model needs exponentially more training samples to find patterns. The manifold hypothesis suggests that chaotic, high-dimensional data actually resides on a simpler, lower-dimensional structure, or manifold. Deep learning succeeds by automatically identifying and unfolding this manifold, ignoring empty space, and finding the true underlying pattern. The three pillars of generative architecture are GANs, VAEs, and transformers. GANs engage in a minimax game to create synthetic data. VAEs use probabilistic decoding for blended variations. Transformers use self-attention to process entire sequences in parallel. The prime number challenge reveals AI's hard boundary. Deep learning acts as a pattern matcher on compressible reality. However, primes are cryptographically random and lack lower dimensional symmetry. AI is a manifold explorer and fails entirely at predicting true random sequences. The feedback loop of doom describes model collapse. When a generative model is trained exclusively on synthetic output, the underlying data geometry degrades. Without human-generated ground truth, successive generations amplify errors, leading to total structural collapse. The heavy cost of virtual computation includes energy consumption, copyright disputes, and societal disruption. Global AI emissions could soon rival major industries. AI-generated outputs often lack human authorship, and RAG poisoning threatens information integrity. AI is an engineering discipline constrained by physics, geometry, and mathematics. By understanding its mechanics, we strip away the magic. AI is the ultimate engine for mapping compressible reality, and our mandate is to guide it with rigor and a clear view of its limits.